Okay, welcome back from the break. Joining us now to present is Vangelis Tasoulas from Simula, who will be presenting prototyping live migration with SR-IOV supported InfiniBand adapter cards.
Hello all. Well, as Brian said, I'm Vangelis Tasoulas. I'm just going to present you a prototype we have made for live migration with SR-IOV supported InfiniBand HCAs. Before I start, I would just like to give some acknowledgements to the people who worked for this project. And mostly, I just have him in a separate bullet, Waylin Guay, which this is mainly his work. So today I will present on behalf of him because unfortunately he couldn't make it here. And to be honest, I have to say this, I'm not very familiar with all of the terminology that it will follow. Some of the slides, most of the slides are made by Waylin, but I will just try to do my best. So this is the outline of the presentation. First, it's an introduction. We will just see briefly about migration and why SR-IOV and what SR-IOV is as well. Maybe some of you don't know. Then, what is the problem on combining live migration and SR-IOV with InfiniBand? Then we will see how the problem is solved with Ethernet devices instead of InfiniBand. And we will go through and see why the same cannot be applied for InfiniBand. We will go through the 4 challenges that makes this not feasible at the moment. And the 2 potential approaches, which is the bottom-up approach and what this work is following, and the top-down approach where the upper layer protocols. And it must be application aware, the top-down approach. And eventually we will come with a summary. So why virtual machine migration? Virtualization and consolidation is 2 things that they are closely tied. And migration enables further consolidation. So by moving more virtual machines on top of less physical machines, then we just solve partly the problem of underutilization of physical machines. And also workload distribution can be another case. When, for example, we have some service level agreement with customers and we consolidate too much, then we can just move some virtual machines away and keep the SLAs. Also service availability, maybe some of our physical servers need to be maintained, so we just move the virtual machines, we migrate the virtual machines to another physical host, we bring the host down for maintenance and then back, and then there's not much downtime. And also, this is quite trendy, the greener data centers with resource overcommitment, and that goes back to server consolidation. So basically with resource overcommitment, we can just put more virtual machines on top of one physical hardware, with the assumption that not all of the virtual machines will use the maximum resources at the same time. So VM migration can be categorized as cold or hot migration. The cold migration is the traditional and simple way to migrate a virtual machine. We need to shut it down and then move it to a destination host and then boot it up again. No problems here, even with InfiniBand. But that's not very desirable in live environments that we want to optimize the workload. So in this case, we want to just go for hot or especially live migration. So live migration is when we migrate a running instance with a minimal possible downtime. And this is also transparent to the running applications. I'll just talk a little bit more later about this. So why SR-IOV and what is it? First of all, IOV, which stands for Input-Output Virtualization. Just a very brief definition is the way hypervisors utilize hardware resources and serve them to virtual machines. And common techniques can be emulation, paravirtualization, pass-through, and the SR-IOV that we are using here. All of them, they have benefits and disadvantages. If we start with emulation, emulation means emulating hardware purely into software. This gives us great flexibility in the virtual machines, but and scalability as well, but it's not very efficient. It adds too much CPU overhead because the CPU has to emulate hardware. For example, Intel Ethernet adapter. And also due to this emulation, we can't achieve very high speeds. Paravirtualization is an improvement of emulation that we can achieve better speeds. But it has a disadvantage that the virtual machines needs to be modified. Basically, we need to install special drivers to understand that this machine is paravirtualized. Then pass-through, it's basically passing a PCI or PCI Express interface through to the virtual machine, and then the virtual machine gets direct access to the hardware. This gives us near to native performance, but unfortunately pass-through is not scalable at all. Because just imagine if you have 10 virtual machines on top of a hypervisor, then you would need 10 adapters, 10 InfiniBand adapters or 10 Ethernet adapters in this case. So here comes the SR-IOV, which I just have a quote there from the PCI SIG consortium. So what briefly SR-IOV is, it allows multiple operating systems, as it says here, running simultaneously within a single computer to natively share PCI Express devices. And the SR in front, single root, is focused on single root topologies. So the SR-IOV introduces the idea of physical functions and virtual functions. So just imagine each PCI Express card is the physical function itself, and it can have theoretically up to 256 virtual functions, basically some up to 256 virtual instances of itself, that these can be passed through to the virtual machines. And then the virtual machines get direct access to the hardware. The difference between the physical function and the virtual functions basically is that the virtual functions have access to a limited set of the PCI Express functions, basically only to the data transfer functions and not to the configuration functions. And since it's a pass-through and the virtual machine gets direct access to the hardware, then again we just get improved performance in virtual machines and less CPU overhead comparing to other types of IOV, and also we solve the scalability problem because with one card, maybe with one InfiniBand card, which can give us a few gigabits per second, we have a big pipe, and then we can just split it to many virtual machines. But what's the problem? Unlike the emulated or paravirtualized devices, the physical devices cannot be paused to save and restore their hardware states, so a consistent device state across live migration is impossible using any kind of device pass-through. when we do migration, what's happening there is that we just start copying the memory contents over from the host, the first physical host, to the destination physical host. So when we have copied all of the memory contents, then we just switch also the network connectivity to the new machine, and that's how live migration happens, and we have the minimal downtime. So at the moment that we still copy memory contents, the virtual machine is operational. That means that when we use emulated or paravirtualized devices, since these are emulated into the software, these devices are stored into the memory. So even the internal device state, which might be some registers, for example, these would be copied over to the remote hypervisor. But when we use SR-IOV, because the device speaks directly to the adapter, the network adapter, the InfiniBand in this case for us, the internal state of the card cannot be copied over, so this introduces problems. So how this is solved for Ethernet SR-IOV virtual functions? In this work, I have the citation here. What they do is that they use the hot plugging mechanism together with a Linux bonding driver to maintain the network connectivity during the migration. So what they essentially do is that they use the bonding driver, and they have two interfaces. One is the pass-through interface, the virtual function, and another one is an emulated or paravirtualized device. So they prioritize the traffic to the virtual function, so they get the maximum performance. And when it comes to migration, that they need to detach the virtual function to move the virtual machine over, the connectivity goes through the paravirtualized or the emulated device. That this device can, its internal memory state, it can be copied easily. So when the virtual machine moves to the remote hypervisor, then a new virtual function is reattached, then again the traffic goes through it. Also in another paper here, just to solve this kind of problems, it has been proposed an extension to the SR-IOV specification, where the internal virtual function state can be cloned when we migrate VMs. But unfortunately, if we try to apply the same solution with the bonding to InfiniBand network, that's not possible. Initially, there's no Linux bonding device available yet for InfiniBand network. But the real problem as well is that in InfiniBand we do not only need to maintain the hardware state, the SR-IOV state, but we also need to keep track of the Q pairs. And you will eventually see that mostly everything is all about it's all about Q pairs, that they introduce most of the problems. And also the addressing is assigned by the subnet manager. And here I just mentioned also the shared port model. With the shared port model, the Q pair context cannot be reused after migration. For InfiniBand SR-IOVs, there are two models for virtual functions, providing virtual functions. The shared port model is the one that we are also using in this experiment, because the cards that we were using, the Mellanox Connect X2 cards, they use the shared port model. And basically the shared port model, only the physical function has an address. So basically the physical function and the virtual function, they share the same lead and the same Q pair context. In the virtual switch model, that it's another model noted here. Each virtual function and physical function, they have their own lead and their own Q pair context. But if you want to find out more again, you can just take a look at this presentation. So that's the hardware and the software we used in the experiment. We have two hosts, host A and host B. These are the hypervisors or the virtual machine monitors you see here. So they are connected through InfiniBand. And the tests were made on top of an Oracle VM server. You saw also in the beginning many people from Oracle have worked in this project as well, which uses a Zen-based hypervisor. And each of the virtual machines, it uses two virtual CPUs and 512 megabytes of memory and one InfiniBand virtual functions. And also inside the virtual machines, we run the IBRDMA bandwidth test utility, just to see the behavior when we migrate. So when we have a virtual machine A here, VMA, in host A, and then we want to migrate it to host B, that's over the InfiniBand. Instantly we're running the first problem, that we are not allowed to move it if the virtual function is not detached. And this is not an InfiniBand problem per se, but it's a PCI prerequisite that the device needs to be quiesced before hot swapping it. So a workaround, of course, is to detach the virtual function, right? But if we just try to detach a virtual function, but there's an active Q pair, an application is running and it has an active Q pair, then how are we going to do it? Because we need to quiesce it first. So in InfiniBand, most of the applications are calling the IB user verbs. And the user application basically can operate directly on a Q pair. What the user application does is sends work requests to this Q pair, to this opaque handler, and then this is forwarded directly to the hardware. In contrast to the Ethernet operations that they require to go through the kernel software stack. That happens because in InfiniBand, much of the work it's offloaded inside the network card to achieve these extreme speeds that we can achieve with InfiniBand. So all of the IBU verbs needs to be released before the module can be unloaded to quiesce the PCI Express. But if a Q pair exists, then trying to detach it, it will return with an error because the Zenfone plugin script will time out. So how are we going to just suspend the application and remove this module eventually? So in this work we have proposed the process ID to Q pair number translation table. So whenever a new Q pair is created, the process ID of the user application will be registered in the kernel. And before the module will be removed, the kernel will signal an event basically to suspend the operations in the user space library. Then when we try to remove it, the wait for completion of function will execute it successfully and the virtual function will be able to be detached from the virtual machine. And also in order to prevent further operations, the communication needs to be halted at the user space. Now we have detached the virtual function and moved it over to the host B. We have migrated. And now we need to reallocate the InfiniBand communication resources. The newly attached virtual function contains a new virtual GUID. This ideally it should be kept the same, but that's the default when you just move it to get a new virtual GUID. And we use it like this for simplification of this prototype. And that means that at the moment, because this VGUID is changing, also the GID is changing. So migration is not possible between different subnets, so only in the local subnet, InfiniBand subnet. But as you see here, the user application, it was talking maybe to a Q pair A. So when we move it, due to the shared port model that as I said earlier, the shared port model shares also the Q pair numbers. This QPA might already be in use by another application, maybe from a different virtual machine. But the user application doesn't know that a new Q pair has been assigned, so it still tries to talk to Q pair A. So the second problem now is how the user application can continue to operate after we migrate the virtual machine by talking to Q pair A, which is now actually Q pair B. So after the new virtual function is reattached, the physical resources such as memory region and the completion queue and the Q pairs must be recreated. And then what we do, we include a user process mapping table to remap the physical resources with Q pair A's Q pair number and to replace the remote and local keys in the posted work requests. So what is this user process mapping table? This has been implemented in the user space library. And essentially it's just a translation table. So the application is still talking to the Q pair A, which initially was assigned to this Q pair number. This is the opaque handler that is exposed to the application. This is the Q pair number in the hardware. So the application will still post job requests here, and then in the driver we just migrate it. We just redirect these requests to the actual Q pair that it's assigned. Simply as that. But before we migrate, if we had any outstanding operations, then we need to handle them. We need to resume these operations, right? So the problem is here, how do we handle the outstanding operations that are in the send queue after we migrated the virtual machine? So we propose the deterministic state for migration. We simulate the send queue drain like Q pair state in software here, because the SQD state is not supported by the connectX to adapters yet, and this yet is a bit old because this is like maybe 1.5 years old work. I don't know if something has changed now. So what the send queue drain like state is that we just make sure before we migrate that there's nothing in the send queue. Basically, we serve all of the work requests, and then the send queue is drained. So the work queues are in a quiescent state before we migrate, and this is applicable to both sides because if this VMA is communicating with something, then it has to also a remote virtual machine or a remote machine in general has to know about this, that we are going to migrate. So after we have received all of the completion queue signals, then we can detach the virtual function from the host A. And eventually, when we migrate, there are no outstanding operations. But now, looking from the perspective of the peer virtual machine and the peer Q pair, as I said, when we are here in the beginning in host A, maybe the virtual machine A communicates with VMC, and Q pair A communicates with the Q pair C. So, when we migrate, this Q pair C doesn't know anything about this Q pair B, that it still knows about Q pair A. So how to reestablish a remote connection? The communication manager must be tolerant to device removal fault. So when we just remove the virtual function, the QPRC from this machine must not be destroyed. And how we make also, how are we sure that this will not happen? And then before the virtual machine A will detach the virtual function, it will send a signal and notify this virtual machine that I'm going to migrate, and so this virtual machine will just do a similar operation to just go into the SQ drain-like state. So we also suspend the communication from this side. And we do that to avoid transmitting into the error state by sending to a non-existing QPR. We also need to keep track of the out-of-band communication used by the communication manager. And then after the new virtual function is reattached, the QPR bin in this side will initiate a connection backwards again to the QPRC, and we will resume the operation. Now, so far, all of this is from the perspective of the virtual machine itself, because obviously we need the virtual machine to cooperate in the current prototype. But from the hypervisor perspective, a typical three-stage migration process is performed to migrate the virtual machine. So first we detach the virtual function, then we migrate the virtual machine, and eventually we attach a new virtual function. But since we cannot implement the Linux bonding driver workaround hack that it's implemented in the Ethernet, this three-stage migration process leads to a long service downtime. So how can we reduce the service downtime? Some small modifications were made in the Zen migration script to allow the migration without detaching the virtual function during the warm-up stage. I just say here a warm-up stage, and also here you see stop and copy. So when we migrate the virtual machine, during the pre-copy stage, we start copying memory over to the remote host. Then we just do some iterations. We also copy the dirty memory pages, basically the memory pages that they have changed during this process. And this is called the warm-up stage. And when we copy most of the memory and we don't have many dirty memory pages, eventually we suspend the VM, that's the stop and copy stage, and we move it over to resume its operation. So during this warm-up stage that the memory is copied over, the virtual function is still attached in the virtual machine. So the communication keeps on running. Yeah, as you see, detach the virtual function just right before the virtual machine is suspended. And then also on the migrating destination, the virtual function at the moment is not initialized during the early restoration, but we attach the new virtual function at the final stage of restoration. Ideally, it should be attached in this case in the early restoration, but then this will need to mess up quite a lot with Zen. So just for simplification purpose, again, we just implemented the late detach. So what I just described you is a bottom-up approach. So the bottom-up approach resolved the mentioned challenges. And also the hacks are implemented in both kernel space and user space library. And the migration model remains the same, so not many things need to be changed in the hypervisor at the same time. The three-stage migration process remains the same. This is a timing breakdown of the migration process. So this is the total time, which is almost 5 seconds, as you see. This might be more or less if the virtual machines have more or less memory, RAM. As you see, the pre-copy stage takes most of the time, almost 3 seconds. And the interesting thing to notice here, of course, it's the network downtime, which is 2.7 seconds in this experiment. And as you see, the downtime, it starts right after the warm-up stage here. Because it's where we initiate the PCI detach operations. And this is a benchmark from within the virtual machine with the IBRDMA bandwidth test utility, as I mentioned in the beginning, in the hardware and software that it was used. Here you can notice the near to native performance. That's 25 gigabits per second from within the virtual machine. That's not something that we can easily achieve with emulated devices or when more upper layer protocols are in the middle. This is the downtime here that you see when we have, here it's where we suspend the VM. So up to here it's running on host A, and from here and on it's running on host B. That's the 2.7 seconds, as you see, downtime. Also you notice here this drop. That's actually this moment, especially here, exactly here, it's when the migration starts. So because we just start copy the memory contents over, and because the virtual machine gets extremely high speed, it's utilizing almost the whole bandwidth of the channel. Of course, some of the bandwidth has to be allocated to the hypervisor because they have to share it, right? So this is when we start copying the memory contents to the destination hypervisor. There is also the top-down approach. We haven't done much in the top-down approach. And we don't need to do much in the top-down approach. We just use it as a comparison here. So the top-down approach assumes that the complexity of the underlying InfiniBand verbs is a black box, and then the failover mechanisms are provided by the upper layer protocols. And in this test, we use the RDS, Reliable Datagram Socket protocol, as the upper layer protocol. That it's also tolerant to faults, including the device removal fault. Again, the live migration in this small test is based on the 3-stage migration process. So what happens is when the virtual function is detached, the protocol will drop the connection, then the VM will be migrated, and then the protocol will reconnect the connection. But the problem also with the top-down approach is that it's not generic, because it depends on an upper layer protocol to support live migration. And for example, what if your infrastructure doesn't use any upper layer protocol that supports fault tolerance? First of all, instantly you will notice the much less speed here, performance, it's much lower. That's due to an extra layer, so more overhead. Also in this case we have a little bit more downtime, but yeah, and it's not so smooth. But the important as well here, it's the extra overhead added by the upper layer protocols. So to summarize, the bottom-up approach provides a generic solution. It can be used anywhere. The current prototype has a service downtime of 2.7 seconds, which is not acceptable still for high-performance computing and InfiniBand, especially when we use the reliable communication. This is more than the timeout. So how do we believe that we can improve the service downtime and the reconfiguration? So we think that the virtual switch model is a better architecture. With a virtual switch model, because the queue pair namespace is isolated per virtual function, this would make things a lot easier, because we would know that, for example, when we move the virtual machine, the queue pair A is not induced by someone else. It's also better model from networking and routing perspective, but also it has some scalability issues. Because, as I said also in the beginning, each virtual function in the virtual switch model, it has its own lead and its own queue pair context, and the lead space at the moment is only 16 bits. So if you just do the calculations, if we could achieve the theoretical of 256 virtual functions per interface, at the moment the real value is 64, but let's go with the theoretical max. Then with a few hundreds of interfaces, we would fill the lead space. And also a new state to define the suspend maybe should be introduced in the hardware, just to make InfiniBand and more live migration friendly. Yeah, that's all. Any questions?